Hello and welcome to video 4 in this series. Today we're looking at multicore and parallel systems. Let's find out some more. The von Neumann architecture is a sequential or serial processing machine. So one instruction is fetched, decoded and executed, and then the next instruction is fetched, decoded and executed, and so on and so forth. But what if we could process more than one piece of data at the same time? This would dramatically speed up the rate at which processing could occur. This is the main idea behind parallel processing. Parallel processing is the simultaneous processing of data. We can consider parallel processing to be a non-von Neumann architecture. There are lots of different ways we can carry out parallel processing, some of which we've already touched upon in this series. We looked at pipelining in the previous video, so I'm not going to spend a lot of time on pipelining on this video, but if you want to find out a bit more about pipelining, please check out the last video in this series. We can also use what we call array or vector processing, so I'll spend a lot of time on that because we haven't looked at that in any detail. And we've also got this one here, which is multi-core processing. We've looked a little bit about the idea of using multiple cores on a computer system, and we'll just look at that in a bit more detail in today's lesson. Starting with array processing. Some types of data can be processed independently of one another. A good example of this, the classic example, is the idea of processing pixels on a screen. So you can see we've got all the pixels here. Some are green or red or blue or other colors possibly. Imagine a situation where you wanted to make, let's say, all the red pixels blue or all the blue pixels red or so on and so forth. A sequential processor would have to examine each pixel one at a time and apply the processing instruction. So it kind of go, okay, is this red? Yes, make it no. Is this red? Yes, make it blue. Is this red? No, move on. Is this red? No. Is this red? No. Is this red? No. It would have to do it one at a time. This would be very, very slow, especially if you think about the high resolution displays we get on modern computers. However, you can also arrange for data such as this to be stored in an array. A one-dimensional array is, of course, called a vector, and a two-dimensional array can be called a matrix. So again, if you do a bit of maths, I'm sure you're already familiar with this. An array processor, or vector processor, has a number of arithmetic logic units, ALUs, that allow all the elements of an array to be processed at the same time. So what does this mean? Well, we have a look here. This is a very simple example of an array processor. At the bottom, we've got one control unit. There's one. But if you notice here, we've got 1, 2, 3, 4 arithmetic logic units. So the control unit can give an instruction, and that can be sent to 4 arithmetic logic units, and they can then perform the same calculation on 4 pieces of data at the same time. So in this case, they can check 4 pixels at once and change the color if required. Clearly, this is going to be faster than sequentially checking each pixel one at a time. With an array processor, a single instruction is issued by a control unit, and that instruction is applied to a number of datasets at the same time. An array processor is an example of a single instruction, multiple data computer, or what we like to call SIMD. So this is something that will come up a lot. We're going to look at different names for different types of computer systems, and this is what we call a single instruction multiple data system, or SIMD. It's really good technical language, the kind of technical language you really want to bring up into exam questions on related subjects to really show that you've got the knowledge and to make sure you get all the points. We will find that games consoles and graphical processing units, graphics cards, GPUs, make heavy use of array processors to shift all the pixels about on screen. So let's pause for a moment and just take a closer look at graphical processing units, GPUs. So a graphical processing unit is specifically designed to perform the types of calculations commonly associated with graphics. So we've got a couple of examples here. We've got a kind of dedicated GPU that you might plug into your desktop. And then we've got a CPU here that has an integrated, CPU. I'm going slightly silly here. This is an example of a simple kind of graphics card that you might find in a laptop. This is the GTX 680M. The M is for mobile. And this is something you might find on your laptop to give it better graphical processing ability. GPUs have instruction sets specifically designed for the sorts of calculations required in graphical processing. They have the ability to process these pieces of data in parallel. So as I've explained, these are examples of single instruction multiple data systems. They're array processors. So again, they can perform one instruction on multiple pieces of data. For example, checking multiple pixels, as we saw in the earlier example. So you might find a GPU on its own graphics card with its own dedicated memory, or sometimes you might find them just embedded into the CPU, sharing the general system memory. So sometimes students get a little confused between CPUs and GPUs and why we have two different systems. So in brief, your central processing unit, or CPU, is very good at dealing with complex problems that involve small data sets. Whereas a GPU is very good at performing simple problems, but on very large data sets. So they kind of work in conjunction because they're just better at different things. So again, if you think about games, you're just throwing all those pixels around. The problems that it's being asked to solve, your GPU, aren't that complicated, but it has to do with lots of data at the same time just to make sure you can keep up a really good frame rate. That's why GPUs are good at that sort of application. While designed for graphics, so for example animation, design, or gaming, GPUs are increasingly being used in many other fields. So this is quite good because in exams and exam questions, you might often be asked to explain why one particular field would use a graphical processing unit when maybe it's not an obvious choice. So you really got to think outside of the box a little bit. But good examples of using GPUs for non-graphical processing are modeling physical systems. So if you think of something like the weather, or particle physics, or cosmology, or something like that. Audio processing, cryptography, breaking passwords, brute force cracking multiple combinations of passwords. Machine learning, AI, these are all problems that can make use of the type of single instruction multiple data system that's kind of built into a GPU. Now let's look at some of the limitations of array processing. This architecture relies on the fact that the datasets are all being acted upon by a single instruction. So although it's multiple items of data, there's still only one instruction that's being carried out on all of them. If these datasets somehow rely on each other, then you cannot apply parallel processing. So for example, if data A has to be processed before data B, then obviously you cannot do A and B simultaneously. So not every problem can be processed in parallel in a way that would be suitable for this sort of processing. Also, it cannot process multiple instructions on the same piece of data. So remember, it's single instruction, multiple data, SIMD. If you remember that, that'll help you think about the limitations. It's one instruction on multiple data. In some situations, maybe it's the other way around. You need to perform multiple instructions on the same piece of data, and this wouldn't be accepted. Now, this is a really good thing to think about, because when you get longer kind of exam-style questions in your exam, longer essay-style questions in your exam, you'll be expected to show evaluation. And that's when you really think about strengths and weaknesses and comparisons. And being able to talk about limitations will help you pick up a lot of extra marks. Let's move on. Let's take a look at multi-core systems. We've already covered that in a little bit of detail in the previous lesson. Let's now look at that in more depth when it comes to parallel processing. So the next level of parallel processing is to have multiple instructions acting upon multiple data sets. This is achieved by having a number of CPUs, or processing units, being applied to a single problem, with each CPU or each core carrying out only part of the overall problem. A multi-core computer is a multiple instruction, multiple data computer, what we call MIMD. So we looked at vector processing, array processing, which is single instruction, multiple data. Multi-core systems are multiple instruction, multiple data systems. So again, you can see here we've got a problem that is going to be divided between all 4 CPUs or all 4 cores inside a CPU, and then that problem can be run in parallel. So they're all running the same problem, but it's been divided up between these cores so it can be processed more quickly. So nowadays, even the humble CPU in your personal computer, your laptop, your mobile phone, your tablet is almost certainly going to have multiple cores. So for example, the Intel i7 chip has 4 cores, while something like the AMD Ryzen 1800X has 8. Even a budget chip like the Intel i3 is usually a 2-core system, so it's still going to be running a multi-core system. And this is slightly out of sequence. Okay, I'll just go back and do that all at once. So MIMD, multiple instruction, multiple data, takes place on a much larger scale when we think about supercomputers. Supercomputers are massive parallel processing machines. So at the time of recording, the most powerful supercomputer in the world is the IBM Summit supercomputer. This has, wait for it, a total of 9,216 CPUs. Each CPU has 24 cores. So each CPU has 24 processing units built into it. So you can do the math, that's a lot of parallel processing. On top of that, it's got graphics cards all over the place. It's got 27,648 GPUs. So it can do it can be single instruction, multiple data, multiple instruction, you've got all kinds of combinations possible. So supercomputers are great examples of MIMD systems because they're massively parallel. This type of computing is applied to problems that are really complex, that would be really beneficial to running multiple processing at the same time. So things like predicting climate change or weather, cosmology, running simulations about new drugs, anything like that, cryptography, all those kind of things are really well suited to running on these massive multi-core systems. We're looking at situations where a large problem can be broken down into smaller subproblems, and these can then be processed in parallel. However, there are limitations again. This architecture is dependent on being able to cut a problem down into chunks, and each chunk can then be processed independently. And not all problems work that way. So an example of a problem that would work very well on a parallel system is the example of adding a billion numbers. So if you're running 100 cores or 100 CPUs, you've got 100 processing units. The first processor could add the first 10 million numbers, the next could simultaneously add the next 10 million numbers, and so on and so forth. And then at the end, the totals are added together. This would take nearly 1/100th of the time on a 100-core system than it would take a single processor to do. That's pretty easy. It's a situation that can be easily run in parallel, so a kind of system that has 100 CPUs would run it roughly 100 times faster than a single-core system. However, as I said, not all problems can be run in parallel in this way. So a good example of this would be running something like the Fibonacci sequence. As we should know from math, each Fibonacci term is generated by adding the previous two terms together. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 5 and 8 is 13, so on and so forth. As each term depends on the previous term, having more processing power available will not speed things up. So if you're running this on a dual-core, quad-core, 100-core system, you're running it on a supercomputer, it's not really going to be running much faster because it can't be run in parallel to the same extent as the adding a billion numbers together problem. This is what we know. This comes under what we think of as Amdahl's law, and this tells us that performance will be limited by parts of a problem that cannot be run in parallel. So Amdahl was a researcher, I think in the 1960s, looked at basically how we can use multiple core systems, multiple CPU systems to speed up calculations of certain tasks. So in this graph, you can see we've got how much we're going to get the speed up, and then we've got the number of processors here, and we've got different examples for how much of a problem can be run in parallel. So if you can see if most of a problem can be run in parallel, you'll get quite a lot of speed up, but eventually you're going to reach a limitation. It's going to plateau. If only a small part of the problem can be run in parallel, you're not going to get a big performance increase, even if you're running a huge amount of processors. Furthermore, the software programmer has to write the code to take advantage of a multi-core CPU system. This is actually quite difficult, and even now a lot of the applications running on, say, an Intel i7 with its 4 cores do not make use of all the cores at the same time. It needs to be a demanding task that's specially written to take advantage of all those cores, that it can divide the problem up so that it can be run in parallel. And again, even today, a lot of applications don't make efficient use of multi-core systems. So imagine trying to write software for a supercomputer where maybe it has to make use of hundreds of processors or thousands of processors. You've also got the basic cost effect. Having lots of CPUs or having a CPU that has many cores in it is more expensive than just having a single core, single CPU system. So running multiple processing units is more expensive than running a single processing unit. Just the hardware is more expensive. One more thing just to take a look at is what we would think of as distributed computing. So this is a new way of doing parallel processing. And again, you can consider this a non-von Neumann architecture for the purposes of your exam. So over recent years, an alternative approach to parallel computing has become viable thanks to the internet, what we call distributed computing. In distributed computing, each computer across a network takes on part of a problem. So in this diagram here, you can see we've got one big task, and we've divided it into 3. 1, 2, 3. Part 1 can be processed by one computer on a network. Part 2 can be processed by another computer. Part 3 can be processed by another. And then when they're finished, they can return the solution back to the master computer. And then we can kind of continue doing that for the next set of problems. So obviously, the more computers you have, the more you can split the problem up. And if this problem can be run in parallel, you can almost get a supercomputer by adding lots of different machines together on the same network. Now, obviously, there are some issues with that. You've got to have a reliable internet connection or a reliable network. You have to have software that's specially written to be able to handle dividing a problem up between multiple machines and then putting the results back together again. But again, it's quite a simple way of having a massive parallel computing network without necessarily needing a supercomputer. Let's just look at some comparisons of parallel processing versus classic von Neumann architecture. So advantages: faster when handling large amounts of data, with each data set requiring the same processing. So this is true for array and multicore systems. Parallel processing is not limited by bus transfer rates, the same the von Neumann bottleneck, in the same way. Parallel processing can make maximum use of the CPU in spite of the von Neumann bottleneck, and that's for pipelining. So if you remember, with pipelining, we are executing different stages of the fetch, decode, execute cycle at the same time. So even though that might be a single instruction, single data system, we can still, using pipelining, we can still do like one fetch, one decode, and one execute at the same time. We can't do two fetches or two decodes, but we're still making maximum use of the CPU despite the von Neumann bottleneck. Disadvantages: only certain types of data are suitable for parallel processing. Data that relies on the results of previous operations cannot be processed in parallel. For parallel processing, each dataset must be independent of each other. It's more costly in terms of hardware. Multiple processing blocks are needed, and this applies to all three methods. You've also got the idea it's just more complicated to program software to run in parallel. So the software development costs are higher, maybe you need better quality programmers. And here is a quick summary of some types of parallel processing. Again, just to show you it. So pipelining we mentioned more in the last video. This is an example of a single instruction, single data system. We can find it inside a CPU, and again, it's a simple form of parallel processing, but can greatly increase CPU efficiency. Array processing is single instruction, multiple data. We usually find that in graphics cards and games consoles. And we've got multicore systems, which are MIMD, or multiple instruction, multiple data. You can find those certainly in supercomputers, but also in modern multi-core chips that we find in every computer we use nowadays. Hopefully that's reasonably clear. Feel free to play the video again, pause it, replay it. Fine, if you can't still get it, go look at other people's YouTube videos as well. Research your textbook. Really important to get used to this, because this is the kind of question where you might get that really long kind of in-depth essay style question where they ask you to talk about non-von Neumann architectures. So it's really good if you can memorize the key points, think about your knowledge and understanding, think about how it's actually applied in real life, and think about how to evaluate the different methods. I'll be back in a week or two, and we'll continue looking at CPUs and all the kind of related technology.
This is an S1 Perry production. Please like, please subscribe, click the little ringing bell thing if you really feel like it. Good night, and good luck.